In this program, we'll be looking at three types of belt-driven power transmission drives: flat belts, V-belts, and timing belts. Each of them transfers mechanical power from a source, the driver unit, to another component in the system, the driven unit. They also perform other important functions. For example, they may increase or reduce the speed of a driven unit using pulleys or sprockets. They also allow the driver motor to be positioned away from the driven unit. And they allow one motor to provide power to several driven units at the same time. We'll take a look at an example of each type of belt to see how they are constructed and how they are used. Let's begin with flat belts and V-belts. Both these types of belts rely on friction to transmit power from one pulley to another. To create that friction, the tension on the belt must be carefully adjusted and maintained. A belt without enough tension cannot transmit power from the driver unit to the driven unit efficiently because it cannot grip the pulley surfaces well enough to prevent slipping. These types of belts operate well over short or long center distances, and they also cushion motors, shafts, and other components against the effects of load changes. The mechanical power a belt can transmit is affected by the arc of contact, as well as by tension on the belt. The arc of contact is the number of degrees around the pulley where the belt is in contact with the pulley. The greater the arc of contact, the better the grip of the belt on the pulley. For example, if both the driver and driven pulleys were the same diameter, then the belt's arc of contact would be 180 degrees. The belt would transmit very nearly all the power, almost 100%. But if one pulley is smaller and the arc of the contact falls to 120 degrees, then the power transmitted will fall to about 83%. Belt sag is a good example of the effect of the arc of contact on drive efficiency. Even when a belt is properly tensioned, there will be some sag. If a belt sags away from the pulleys, the arc of contact is decreased and power is lost. To prevent this, an idler pulley may be used. This prevents sag and increases the arc of contact. When a belt sags toward the pulleys, the arc of contact is increased and an idler pulley may not be required. Let's take a closer look at how these belt-driven friction drives operate, beginning with flat belts. In the past, leather has been used extensively in flat belts. Today, however, most flat belts are manufactured from rubber, natural fiber, and synthetic materials. A rubber belt, for example, is normally constructed by coating canvas with rubber. The coated canvas is combined with alternate layers of rubber sheeting, then vulcanized to produce the belt. If the edges are wrapped around the canvas, the belt is called folder edge. But if the edges are left ragged, then trimmed back to make them square, the belt is identified as raw edge. The canvas provides strength when the belt is under tension. Some belts are stitched for extra strength, although the rubber bonding is normally sufficient to hold the belt together. Another type of belt is the woven belt. These belts can be composed of cotton or synthetic material, either coated or uncoated. Usually they have stripes running lengthwise to indicate the number of plies in the belt, one stripe for each ply. The ends of both leather and cotton belts are connected by lacing the ends together or by fastening them with steel clips or wire hooks. Some need a special machine for installation, while others need only a hammer. Flat belts made of synthetics like nylons and polyesters are becoming more common. Since they can have a very thin cross-section and still be as strong as other flat belts, they can be used on very small pulleys at high speeds. However, since they are so small, they can't be joined by the clips or lacing used on standard belts. Instead, they must be bonded into endless belts by the manufacturer or with special equipment. V-belts are the most widely used drive in industry. They are easy to install, require little maintenance, and operate in a wide variety of environments without needing lubrication. However, because they are so reliable, people often take them for granted and fail to follow proper installation procedures and maintenance practices. The V-belt gets its name and its gripping power by wedging its V shape against the inside of the groove in a pulley, usually called a sheave. When a V-belt is installed, tension is applied by adjusting the distance between the drive motor and the driven equipment. Usually the motor is mounted on an adjustable base which is moved away from the driven equipment. Tension can also be adjusted by using an idler pulley, which may be used to adjust slack or sag and may apply additional tension to the belt. The harder the belt is pulled against the sheave, the more gripping power there is, and the less tendency there will be for the belt to slip. If the belt does slip, heat is created. This causes the belt to stretch, creating more slippage and more heat. The cycle will continue until the belt burns up or turns over in the sheave. Improper belt tension is by far the most common cause of belt failure. In addition to tension, the condition of the sheaves and their alignment can also affect belt performance. If the sheaves have burrs or rough spots, the belt will be gouged and it will wear out faster. If the drive is misaligned, the load will not be distributed evenly across the belt. As a result, some parts of the belt may wear faster than others, and the belt will fail sooner than it should. To align the drive, stretch a clean white string between sheaves or use a straight edge. The string or the straight edge should touch 2 points on each sheave. When the driver and driven units are far apart, better results may be obtained with a string because any deflection is easily seen by sighting along the length of the string after it is in place between the sheaves. Long, accurate straight edges are sometimes difficult to locate. Not all V-belts are exactly alike. The conventional or classical belt is still the most common, but the narrow section belts are also available. Even though they are smaller, their load-carrying capacity may be the same as a conventional belt. Both kinds of belts require their own special sheaves, and they are not interchangeable. Cogged or notched belts permit easy bending and tight turns around small sheaves. They usually have raw edges to give them extra gripping power on the sheave. The link belt is made of individual links, which can usually be replaced without having to alter the center distance between the driver and the driven units. And if a belt is damaged, single sections of the belt can be removed and replaced easily. Ribbed V-belts have a true V shape rather than the flat bottom design of the conventional V-belt. They have added strength because they need about 20% more tension than a regular V-belt. They also require special ribbed sheaves, which must be more carefully aligned than conventional sheaves. Banded V-belts are really 2 or more belts joined by a layer of rubber and fabric. This connecting layer helps to stabilize the belts and to keep them working as a set. When working with multi-belt drives, it's important to remember that belt designs should not be mixed. In addition, the belts should be all from the same manufacturer because different belts may require different amounts of tension. If belts of different design or from different manufacturers are mixed on the same drive, some belts may be over-tensioned, others under-tensioned. When this happens, the over-tensioned belt will carry most of the load on the drive and will fail much sooner than if the belts were matched and properly tensioned. Now, let's take a look at timing belts. Unlike flat belts and V-belts, which rely on friction to transmit power, timing belts rely on teeth that mesh with a sprocket. The teeth and sprockets provide a positive transfer of power, slipping only under extreme shock loading. Timing belts come in a wide range of sizes, but all of them have 4 basic parts: the tension member, the neoprene backing, neoprene teeth, and nylon facing. The tension member, the muscle of the belt, is usually made of carbon steel or fiberglass. It provides the strength needed to prevent the belt from being ripped apart while the drive is operating. The neoprene backing of the belt is the layer just above the tension member. It protects the tension member from grime, oil moisture, and frictional wear. The teeth are usually made of a shear-resistant, moderately hard neoprene compound. The teeth are very strong. In fact, as long as 6 or more teeth are meshed with a sprocket, an extreme load will tear the belt apart before it strips off teeth. An important term to understand about the teeth is pitch. This is the distance between 2 identical points on adjacent teeth. It is measured along the pitch line, an imaginary line that could be drawn through the middle of the belt. Timing belts are available in many lengths and many widths, but usually only 5 standard pitches. Each belt is stamped on the back with a code that indicates the belt's length, its pitch, and its width. The first section of the code indicates the length of the belt is measured through the pitch line in inches. In this case, the length is 24.0 inches. The middle section of the code is the pitch, in this case, H, which stands for a pitch of 1/2 inch. That means the teeth are 1/2 of an inch apart. 5 standard pitches are commonly available. XL, or extra light, with a pitch of 1/5 of an inch. L, or light, with a pitch of 3/8 of an inch. H, or heavy, with a pitch of 1/2 an inch. XH, or extra heavy, with a pitch of 7/8 of an inch. And XXH, or extra heavy, with a pitch of 1 1/4 inches. The third part of the code indicates the width of the belt, again in inches. In this case, 1.00 means 1 inch. The last part of the belt is the facing, which covers the teeth. Normally, the facing is nylon. Under normal service, it polishes to a slick, shiny appearance. Although this facing is the only part which is subject to much friction, it will normally outlast the other components of the belt. Timing belts use sprockets that are very different from the pulleys needed for flat belts and V-belts. Timing belt sprockets are toothed, and they usually have flanges on both sides of the smaller sprockets to guide the belt. Because of the way they are manufactured, timing belts would run off the sprockets unless the flanges kept them in place. Timing belts do not generally need the precise tensioning required by V-belts. Usually a tight fit is all that's needed, because it's the teeth on the belt that actually transmit the power. An exception is when the drive must undergo very heavy shock loading or reversing service. In these cases, it may be necessary to make the belt relatively tight to prevent ratcheting, that is, the slipping of the teeth in the sprocket. Ratcheting wears out timing belts very quickly. Sometimes during installation, it is not possible to move the sprockets further apart to tension the belt. In these cases, an idler pulley is used to take up the slack and provide the correct tension. Misalignment is also a cause of failure, and care should be exercised during installation to make sure that sprockets are aligned as carefully as possible. Just as with friction belts and pulleys, use a clean white string or a straight edge. Accurate alignment will make timing belts, sprockets, and bearings last longer. Now, there are a few things about all types of belts that you need to remember. To prevent damaging a belt when removing it or replacing it, never pry it off its pulley or sprocket. Move one of the units so that the belt may be slipped off. If it has an idler pulley, move the idler pulley instead. Proper alignment of the pulleys or sprockets is essential if you're going to get the maximum efficiency from these drives. Take the time to line them up correctly. The correct tensioning of all these belts is important, but especially for V-belt drives. Belt dressing is no substitute for the correct tension. Finally, storage. All types of belts should be stored in a cool, dry place and where they will not be creased or bent. In this program, we have looked at 3 types of belts used in power transmission drives: flat belts, V-belts, and timing belts. We've seen how they work, how they're constructed, and we've seen the importance of proper installation and maintenance. No belt lasts forever, but by following the guidelines discussed in this program, unexpected equipment downtime can be minimized.